sort of connections between the kinds of sort of topology and topological, sort of field theories / lattice models that I've been talking about, and symmetries, and also to anomalies, okay? So that's the theme of today's lecture. And I'm going to start, rather than sort of saying general words, I'm going to illustrate this theme with a very particular story, which is a tale of two paramagnets. And so this tale was first told in a paper by Levin and Gu around 2012. And the story goes as follows, okay? So of course, and this is a two-dimensional story, okay? And it starts with a model that I think we all are very familiar with, which is like an Ising model. And for reasons that will become clear eventually, I'm going to draw my 2D Ising model as having spins on the, they're on a triangular lattice, okay? But I'm going to draw that triangular lattice at the center of a honeycomb lattice, okay? And a paramagnet, which I'm sure that you are all familiar with. So a choice of Hamiltonian that I can make for my Ising model on my 2D triangular lattice, which definitely does not spontaneously break the symmetry, is just to leave off the ZZ couplings entirely, okay? And so this is very clearly a paramagnet, right? It's invariant under the Ising symmetry, which of course is just product of all spins x, okay? And we can write down its exact ground state, right? Which is just the eigenstate of poly x with eigenvalue 1 on every site. And this is a paramagnet that is clearly trivial. It's a product state. This is the definition when we say we have like a trivial phase. The ground state is connected adiabatically to a product state. And so that's clearly true here because this is a product state.
So is this triangular or honeycomb?
Sorry, yeah, so my spins are living on the centers, okay, of the plaquette. So they're living on a triangular lattice. Yeah, good. So why did I draw this honeycomb? Because a nice way to think about this paramagnet for us will be that, so I can also represent this ground state in terms of domain walls, okay? So what does that mean? Well, if we sort of focus in on, maybe we'll just draw a couple of plaquettes over here, and I'll make them a little bigger, okay? And so if we focus in on these spins, right, and I look at sort of, so here's Z1, and here's Z2, right? And I can assign a variable to this edge, okay, and let me call it, here I will put an x twiddle 1, 2, okay? And all I want to do is encode the information about whether these guys are the same or different, and I do that by saying that x twiddle 1, 2 is just Z1, Z2. And so on for the other edges, right? And in this language, you might ask, what is the operator x acting on, say, this site at the center of the plaquette? Okay, and you can check from the commutation relations that that is a product over the sites that are neighboring this plaquette, okay, of the variable that anti-commutes with x twiddle, which I'll call z twiddle, okay? And so in other words, this is just a term, right? What does this do? What does this do? If I start with no domain walls, this is telling me if I start with no domain walls around my plaquette, right? And I apply x on site 1, right? Then I get a domain wall all around the plaquette. Perfect, okay. So this is just another way of writing down my paramagnetic ground state, right? And obviously, because these guys are domain walls, right, we can note, right, that the edges where x twiddle is -1, which are the ones that I'm shading or drawing in red, right? So these are domain walls, right? And so these form closed loops, okay? And from here we can see, right, that if you want to be in an eigenstate with an eigenvalue +1 of x on every site, right? So now we can write down our ground state in this domain wall representation, okay? And up to some normalization, it looks like the state with no domain walls plus, a superposition with relative plus signs of all possible domain wall configurations. Okay?
It's not equivalent.
Well, if the Hamiltonian is exactly x everywhere.
No domain walls.
Sorry?
Then there will be no domain walls.
No, these are domain walls in the z basis.
Sorry?
These are domain walls in the z basis.
The Z-way.
So the way to think about this, right, the way to think about, like, in this picture, right, I'm sort of, in my original lattice, I'm starting, this state, right, would correspond to, like, in my original lattice, this would correspond to all up or all down, right? So in domain wall picture, I can't resolve that, right? And then this one, maybe if I have one loop around one plaquette, I flipped one spin. And so yeah, in this, this is exactly equal amplitude. Okay, good. And this state should look familiar, in fact, okay? Because you would notice that this is exactly one of the ground states of the Torah code. Right? Now, why do I say one of? Because in the Ising model, it's not so natural to think about, states like this. So question mark, how to interpret this. This is some section where we have some part of the Hilbert space, right, where I've got some twisted boundary conditions on the spin. So if you wanted to have all four ground states in your Ising model, you would have to think about all of the different boundary condition sectors. We don't need to do that, okay? But you could. All right. So we've made this connection to the Torah code. We've said the Torah code, one of the Torah code ground states, is exactly just the ground state of this perfect paramagnet. And then we might ask, well, can we take this connection a little bit further? Okay. I feel like this marker seems so promising, but it's kind of dying, so we'll try another one. Okay. And you might ask, how far can I take this analogy? And in particular, can I extend this analogy to like excited states of the Torah code, right? And so, let's just look at the level of one plaquette, okay? So plus on some plaquette, maybe I'll call it P, right? So that corresponds to some superposition, and I could choose the outside spins to be in any configuration I want. Let me just choose them all to be up, okay? And so if they're all up, then there's one configuration where there's no domain walls anywhere, right? And then in the ground state, right, the statement that I'm an eigenstate of x with eigenvalue 1 means that I have to add to this, right, the configuration where the guy in the middle is down, right? And when I do that, then obviously I have a domain wall around the edge of the plaquette. And so one excitation, right, that I can certainly have in my Ising model is simply a plaquette on which the eigenvalue of poly x is not plus, but minus, right? Right? And so that would look like this guy. And I'd put a relative minus sign here, right, and have the domain wall over here. And if you remember in the Torah code, this is the excitation that we would usually call M. Okay? Just because in the Torah code we think of these guys. So there's a language confusion that I'm going to try to clarify. In the Torah code, we think about M, and we name it M because we sort of have in our minds, oh, it's a bit like a magnetic flux, and my E particle hops around the plaquette. Okay, now I've put my spins on my plaquettes, okay? And so the M, the thing that was M in the Torah code, in this case becomes the symmetry charge, okay? Why is that? Because the symmetry is just product of all the x's, right? So, which is a product of eigenvalue of x, right, on every plaquette. And so obviously, if you take this on a plaquette, right, xp, if I have a plaquette that has an m in it, right, I get an eigenvalue of -1. And you'll notice that there is, you know, sort of another difference between the toric code and the Ising model, which is that the number of m's in my toric code, if I put it in closed boundary conditions, periodic boundary conditions, that has to be even. These are emergent particles. Whereas nobody told me that in the Ising model, I can't just have a single spin in the minus direction. So not quite the same, but they're very similar. And again, for our purposes, this analogy is going to be very useful. Okay, so we have the m particles. Now, what about the e particles? Right, so the e particles at in the toric code live at vertices. And so those would look like endpoints of open domain walls, right? So here's an e particle. Oh, better get a red marker again, right? So here's an e particle. It lives at the endpoint of some open line, right? It was created with this like string of poly z's, okay? And of course, so it looks like an open domain wall, okay? And these don't exist in the Ising model. They don't exist in the bulk of the Ising model. And people talk about adding, adding this in. We could call these symmetry fluxes, but
That's because of your definition of your x.
sorry?
It follows from the definition of your x1, 2. The product in a closed loop is 1.
That's right. Yeah. And so
Flux, this is like against one.
that's right. So, if you wanted to sort of like weakly gauge the symmetry, I could talk about these fluxes, I could talk about what they do. But, naively, this is not in the Ising model, okay? So this would have the interpretation of a symmetry flux, an open domain wall is a symmetry flux. It's not in the Ising model unless I have a boundary, right? So here's my Ising model, right? Here's the vacuum. I don't know how it's supposed to be an empty set. We'll just write vacuum, okay? And obviously, if I put a boundary on my Ising model, right, then this is totally fine. My domain walls can end on the boundary, okay? Perfect, okay? And indeed, if you think about it for a minute, if you want to pick a boundary condition that is invariant under the symmetry, that flips all of the spins, okay, and that's not a cat state, you better allow your domain walls to end on the boundary, okay? Because otherwise the whole boundary has to be in one domain, okay? And so either it's not symmetric, either it's just all up, or it's a superposition of all up and all down, and therefore it has a degeneracy. Okay. So it can end on the boundary, and it must be allowed to end on the boundary if the boundary is symmetric. Okay, good. All right. Well, so that was like kind of a long description of a Hamiltonian with a trivial product state, okay? So now, but this is going to be useful because now I'm going to write down a Hamiltonian for the second paramagnet, okay? Which looks very similar, okay? I'm going to sum over all of my sites. I'm going to have an x on each site. But now, in addition to this, I'm going to have a product, and I'll draw a picture of where these guys are. Okay, I'm going to have a product going around the plaquette of this funny phase factor, okay? And the easy way to understand what this phase factor does is, so here I have a J, okay? And then this product runs over, this is a J prime, J prime prime. So all of the pairs of sites that make the other two corners of a triangle, okay? And basically what this does, okay, is, so this here, right, this quantity here gives me pi over 2 if there's a domain wall, so a phase of pi over 2 if there's a domain wall, and a phase of 0 if there's no domain wall, okay? And so this basically is a factor of I to the number of domain walls exiting the plaquette J. So that's all this is. So now we can, so for this other Hamiltonian, okay, so this is why it's useful to understand this domain wall picture. For this other Hamiltonian, we can think about the ground state, and it's indeed, so for this one, it's certainly not obvious, like it's not obvious what it is, and it's actually easier to work in the domain wall picture, okay? So remember that, so this is again an operator, okay, from which you can build a projector. And so we can think about building up this ground state, right, by starting with, everybody up, right, in the Z basis, right? And then I'm going to act with BP. And if everybody was up, right, now I'm going to generate a loop. Okay, I had like a minus sign here. Sorry, I think I want to, do I want a plus here? Yeah, I think I want a plus here. Okay, so I want to have an overall minus sign so that when I act with BP, okay, so BP is minus, xp times this phase factor, okay? So I get a minus sign, okay, when I flip a spin and create a domain wall, okay? And basically, so I'm using the fact that you can generate the ground state by starting with the state that's all up, and then just like, applying a sum of products of all of these flip operators to generate all of the loop configurations, okay? Sorry? The BPs commute, yes. It is important, yes. It is important that the BPs commute, and they like square to 1, so it's easy to write down a projector. Yes, I'm using that fact. Yeah, thank you. Good, and so now we can ask, what is the sign structure? So we can see that if I have a single loop, I get a minus sign, and now we can sort of look at other configurations, okay? And we can see, now I'm just going to draw the domain walls, we can see that if I have a plaquette where I have 2 domain walls, right, doesn't matter where they are, right? So now, in addition to the overall minus sign that I had with the loop, I get a factor of I squared, right, 1I for each domain wall. And so here I'm going to get a plus sign, okay? The loop's just going to wiggle. And then we can look at the other ones, right? So remember, the number of domain walls has to be even, so we don't have to think about any situation where we get factors of I here. To think about this bulk ground state. Right, so, and then you can ask, well, what if I have, what if I have 4, domain walls coming in, right? And, it's useful to sort of complete this picture in some way. So, maybe these guys connected up somewhere out here, okay? And now I'm going to apply this, BP. And now I get a factor of I to the 4th, so I again get a minus sign, okay? And now these guys are going to be connected up in the opposite way, right? Something like this. And so on, okay, and then if I have 6, you're again going to get a plus sign. We could draw the loops like this, okay, and then we're going to get What did you say?
It's a three-leg quantum diagram, the string theory picture.
Oh, okay.
Function of time is 1 into 2, or 2 into 1 is 3.
Okay, well, so this one is a plus sign. Okay. All right, all right. To me, it kind of, I don't know, looks like a weird chef's hat or something. So what's the pattern here? Now we can spot it very quickly, right? The pattern is every time I change the number of loops, right? Here I changed the number of loops, here it stayed the same. Here, sorry, I need to really erase this line, right? But here I changed the number of loops from 2 to 1. Here I changed the number of loops from 3 to 1, so I killed 2 loops, right? So every time I add or remove a loop, I get a minus sign. Okay. So that's the structure of this state, right? So, you know, it looks a lot like the Torah code, except it's got some minus signs. Oh boy. Except it's got some minus signs. Okay. Okay, good. Okay. Now, just like yeah, and I guess I should, sorry, so the aside of, you know, what I'm doing here, which I should have written out explicitly earlier, is you can check that, you know, BP commutes with all of the other plaquettes, right? And then also you can check that BP squared is equal to, you know, it's -1 to the number of domain walls on the plaquette, but this is even, right? So it's -1 to the 2 times some integer, which is +1. Okay. So this is how we're building up these projectors. Okay. So this is another state. It looks a lot like the ground state of the toric code, okay? And indeed, okay, so this is also the ground state, or one of the ground states, of some two-dimensional topological order, okay? It's not the toric code. It's called the doubled semyon model. And if you want to learn more about, you know, this construction and many others, this was first described in a paper about string net condensation by Levin and Wen, okay? And they talk about, you know, the operators that make all of the anionic excitations and compute a lot of stuff explicitly, okay? But let me just, I'm not going to go into detail about that, but let me just point out a couple of things, okay? So the first thing is, just like in the toric code, right, we can now ask, you know, which excitations, so all of these things about, you know, the 4 ground state sectors and symmetry even and so on, these are all exactly the same, okay, as in the toric code. But, oops, we can now ask about excitations, right? And we can again make this analogy between excitations that are allowed in our spin model, right? So an M particle, by which I mean a plaquette defect, okay, which, by the way, you will be reassured to know you can write down exactly the operator that creates it. It's not much different than the one in the toric code. Okay, this guy is a boson, okay? And this is, again, just realized, right? This is, again, realized in the Ising model, right? And it's realized by taking, like, a wrong sign somewhere, okay? Which, you know, when we, you know, so wrong sign for every loop that encloses some plaquette would mean that we have an eigenstate with eigenvalue +1 instead of -1 for this guy. So that one's there, but in the topological model, right, so the difference between the topologically ordered model and our, actual paramagnet is that in the topologically ordered model, I'm also allowed to have these symmetry fluxes, okay? And here I'm not going to call them E, I'm going to call them S. And you might want to call some of them S bar, okay? S is for semyon, so we'll get to that in a minute, okay? And so these are the vertex defects, okay? These guys are not in this, sorry, this is not, I should call this paramagnet prime, okay? These guys are not in paramagnet prime, except at the boundary, okay? Good. And now we can ask, okay, so we have these guys, and they should be allowed to end at the boundary. And let me just point out one thing, okay? So these guys are not bosons. And you can see that essentially from looking at this sign structure of these domain walls. And it looks something like this. So suppose that I make one of these excitations, and I'm going to make it here, and then I'm going to ask, and then around here I have some loop. Okay, this should be red. This is some domain wall, okay, that's doing something. And then it's coming around, it's coming like this, say, and then going out. Okay, so it's got this kind of loop. And now we can do a sort of a plaquette move, right? We can flip, if you like, the spin right in here. So I'm gonna do this. And here, this guy is gonna give me a minus sign. Okay, and now we can redraw the picture. And the picture after I've done this looks like this. Okay, and then this loop goes around, and it again comes around this plaquette, and then goes down in some way. And what does this tell you? Okay, this basically tells you. So you could think of this this picture as having. You could think about this picture here. I'm going to erase my red line now, right? Okay, so this is again just something I haven't like applied anything near this guy. Okay, I've just applied the Hamiltonian over here. But the relationship between this picture and this picture is like a double twist. And what do I mean by that? Now let me kind of draw. So suppose that I had drawn the line straight, right? And then I might have twisted it in one direction, right? So I cut out this little, I cut a little point around my annulus, and I just like rotated the rest of space around here, right? And then I got something that looked like this, right? So this is one twist, and of course I could have twisted it in the other direction, right? And that would have given me a picture that looked like, okay, this is not the best picture. That would have given me a picture that looked like this. And we notice that there's a relative minus sign between these, okay? And so here, this is why we call this a semyon, okay? Because basically this tells us that the twist should induce a phase of plus or minus I, okay? So here's how you deduce that just by looking at the sign structure of the ground state wave function. Okay. So these guys are semyons, and so maybe I'll just write down what that means so that everybody is on the same page, okay? Yeah? Oh, why am I doing this? Oh, so what I'm saying is like, okay, so when I call this a semyon, right, what I mean is that this is a particle where like if you take it and you twist it, right, so here's sort of a ribbon diagram in space-time, okay, and my ribbon does a twist, right? So for a fermion, this would get you a phase of pi. For these guys, what this argument suggests is that you get a phase of plus or minus I. Okay, so this is the conformal spin. Yeah, well, yeah, that's right. And so if you like the braiding of these, so this is the twist, right? And so this tells me that the S matrix, okay, the full braiding, right? The thing that looks like this is -1, right? So this would be a diagram. I guess, I would call this a twist and this a braid, but okay. Yeah, so this is what we mean when we say that they're semions. And like I said, this, this is like, I'm not saying this is a rigorous argument, okay? Like Levin and Wen explicitly constructed the operators that make these guys, and then, you can see from the operators, the commutation relations of the operators, that you have this. But this is like a really nice way to think about why this comes about. Okay, very simple argument. Good. All right. Now, and since this is supposed to be a program on field theory, okay? Okay, so this is a doubled semion, okay? And what that means is if you work this out, okay, if you work this out in detail in the lattice model, you'll see that there's actually two of these guys, okay? One gets plus and one gets minus, okay? So you actually have both of them. And another way to say this is if I wanted to write down a topological quantum field theory for this model, right, I would write down an action, okay, which has a Chern-Simons form, okay, and I'll have two fields, maybe I'll call them A1 and A2, okay. And the action looks like this, okay? So this, depends what language you like, right? But this piece here is like a Laughlin nu equals a half state bosonic quantum Hall state, okay? It's like, U1 at level 2, okay? And this is like a Laughlin bar, okay? So it's like, think I put the magnetic field in the opposite direction, also at nu equals a half. Okay, good. And so this action has exactly the particle content that we see in this model, okay? It has a semion, which is the Laughlin quasi-particle here, right? So the semion comes from here. It has an anti-semion, which is the Laughlin quasi-particle here, and it has something that I can create by taking the two and sticking them together, which is a boson, which turns out to be N. Okay, good. So now we would like to know whether this second paramagnet is different from our ordinary Ising paramagnet. Okay. And it turns out that it is. And it turns out that and it is because of the statistics of these S guys, right? Okay. So I'm going to give you a couple of different arguments for this. But let me start with the kind of most pedestrian one, which looks like this. So let's consider our paramagnet prime, okay? And I'm going to put it on a disk, and this is the boundary of the disk. And like I said, if you want this boundary to be symmetric and non-degenerate, then you better pick a boundary condition, okay? Let me draw these in red. Okay, you better pick a boundary condition where these domain walls are allowed to end at the boundary. Okay, this is like mandatory. Now, if this boundary is gapped and symmetric, okay? Then basically, right, so the bulk is symmetric, right? So here I flipped a bunch of spins in the bulk, but what we mean when we say it's symmetric is like, I don't really care. It's this whole like loop soup of domain walls. So putting this domain wall in the bulk, the ground state, you know, doesn't matter, right? We see this explicitly. The way that we constructed our ground state was by, you know, like building a state that's an eigenstate of like adding more domain wall loops, okay? So definitely I should be able to erase this in the bulk, right? And if the boundary is gapped, it has some kind of correlation length, right? Which is finite. And so at most, this can leave some kind of blob, okay? Maybe I should label these points. This is A and B. And at most, it can leave a blob at A and a blob at B. Okay, that's just what it means to be a gap symmetric boundary. Okay, so now let's suppose that I already have this domain wall like this. Okay, here's A and B. And now I'm going to come along and I'm going to make another domain wall with endpoints C and D. Okay, so by this logic, right, if the boundary is gapped, then, you know, all this is everybody has forgotten, right? I acted with this, everyone's forgotten that happened, except maybe these endpoints. But like, okay, C is going to be far, far away from these endpoints, many correlation lengths away, right? And so I have this, like a C and a D, right? And these, again, are just blobs, so we can erase this line. Okay, so if the boundary is gapped, then that has to be true. But there's a problem with this, right? And the problem looks like this. So I also know, right? So I sort of drew this pattern of intersecting domain walls. And if we zoom in, okay, on what's happening here, let's blow this up, okay? So let's blow this up. And here what I have, again, you know, this lives on the honeycomb lattice. And at this intersection, right, I started with, you know, with this domain wall here, and it was like going this way, right? And then I brought along, maybe I'll put this guy in a different color, right? I brought along this domain wall here, and it was going this way, okay? And so then at the end of the day, I, you know, kind of erase this, right? And I made some kind of structure that looked like this. So now let me draw this again on my disk, right? So what I actually have is, you know, something that looks like this and like this, right? Okay, kind of in terms of what's going on in the bulk. On the other hand, right? I could have also had domain walls that ended at the same endpoints, right? That looked like this. Okay, that looked like this, right? And maybe I'll draw these closer to intersecting, okay? And now you can see, actually, that to get from this configuration to this configuration, right, I have to do one of these moves where I'm going to pinch this together, right? I'm going from this to this, okay? And this has a minus sign, okay? But if the domain walls were gapped, right? Sorry, if the boundary was gapped, not domain walls in the bulk, fine, okay? But if the boundary is gapped, right, I would say, well, this also just gives me my 4 blobs. Sorry, I switched the labeling on you guys, okay? right? But there's a minus sign here, okay? So this is what gives us our contradiction, okay? Right, so here I get a minus sign, right? So this is because obviously I can't, you know, this is basically supposed to be two equivalent ways, you know, two ways of generating the same set of kind of domain wall endpoints on the boundary, and clearly because of this sign, these can't be the same, okay? Sorry? No, yes, non-degenerate, yes, yes. So I'm saying gapped and, yeah, and symmetric and non-degenerate, yes, absolutely, thank you, that's very important, yes. Okay, so the conclusion, right, is that there is, so this other paramagnet, right, cannot have a gapped, unique or non-degenerate, symmetric boundary. Okay? In other words, it is what we call a symmetry-protected topological phase, or SPT. Okay. Yeah.
Just the fact that when we gauge it, you get a different topological order is not enough to prove that's a different case?
Okay, so I think what this argument shows, sorry? Oh, the fact that you, yeah, I think that, so there's certainly papers that, you know, basically claim that this is true, and I think it's true. Yeah, I think that's true. So the question, for those of you who can hear, was, you know, is it true that just basically if I have two states with global symmetry, and when I gauge them, I get different topological orders, is that sufficient to ascertain that the states are different as states with global symmetry? And I think so, but there might be some exceptions that I'm forgetting about. Okay. Good, and you know, just sort of as an aside, okay, for people, okay, for those of you who love group cohomology, okay, this is like a side remark, yes.
This is suggesting that the boundary you have a chiral and an anti-chiral.
I will come to that in a minute, yes. I will come back to our Chern-Simons action.
Why aren't they gapped?
Okay, I will answer that question in a minute in a way that hopefully will please you. Okay, but yeah, so let me just make a comment. So, you know, this is a very general argument, okay? And so the moral, right, okay, is if my symmetry fluxes, okay, because really, remember, this minus sign also told us that if we allowed these to be point particles in the bulk, they had, you know, they had non-trivial braiding statistics with each other, okay? So if the symmetry fluxes have non-trivial braiding, okay, then whatever state you're writing down is an SPT, okay? You have this obstruction, Levin and Gu called it the braiding statistics obstruction to having a symmetric gap boundary. Now, if you love group cohomology, H3 of G comma U1, okay, and you would like to know how to essentially take this argument and actually compute the explicit cocycles, okay, there's a very nice paper by Kawagoe and Levin that shows very explicitly how you do this, and they do it in a nice controlled way by actually starting with symmetry breaking boundaries and constructing symmetry actions on them, and you can really extract, using really essentially this idea, the three cocycles. of this. So the SPT is classified by an element of H3 of your symmetry group with U1 coefficients, okay? And you can calculate what that is explicitly, basically using this idea. Okay, yeah.
This model, this SPT do not have this entanglement, topological entanglement, right?
The SPT does not have topological entanglement entropy, yeah.
Yeah, but then there are these models that do have that. They don't have braiding. They don't have braiding. You don't understand. So you're saying if you have non-trivial braiding, then it's an SPT. So it doesn't have.
Okay, but
One sector has non-trivial.
so
When you glue them together, it doesn't.
So when I say, when I add symmetry fluxes, essentially I'm gauging the symmetry, because this is a discrete symmetry, so you're not, well, okay, it's background fields, but what I mean is like, the flux, you know, I can, yes, okay, if it's background, yeah, good. If they're symmetry fluxes, technically we shouldn't be allowed to move them, right? But, you know, because these are gapped discrete gauge theories, you know, like you can gauge the symmetry, there's no extra gapless modes, there's no extra subtleties. And so this is, okay.
Yeah, but you're getting essentially
Well, I guess if you really are adding them as defects and they're line defects, then, okay.
But they're fixed line defects, you're not summing them.
Yeah.
So at any rate, once you write down as a double Chern-Simons theory,
Yes.
each Chern-Simons theory does have topological order. The double theory doesn't.
The double theory definitely has topological order. It does not have a chiral central charge, but it has topological order. So yeah. So that let me explain the argument for that. Okay, good. Good. But did we answer your question?
Yes, but
Okay.
you don't understand. That's another.
Okay. Yeah, I think maybe we should talk about that afterwards, because I don't have a good, I understand why that's confusing. Okay, good. So this is picture one, right? So picture one, so when we have SPTs, right? Picture one is we have braiding statistics of symmetry fluxes. And at least in 2+1 dimensions, you know, I've shown you that explicitly this is a way to characterize the fact that it's an SPT. Now, the other thing, I think John mentioned this in one of his lectures, okay? Another thing that we'd like to talk about when we have SPTs is a different way of sort of characterizing this is through some kind of anomaly inflow argument, okay? Together, and I have to sort of, you know, impose some Z2 symmetry. Okay. So let me start by, and you know, with apologies to those of you who've like done this many times yourselves, okay? But let me start with the most basic example of anomaly inflow, which is what if I just had a chiral Chern-Simons theory, okay? Okay, and here you could choose K to be 1, or you could choose it, you know, to be bigger than 1 and have non-trivial topological order. Either of those choices is okay. And, you know, so obviously I wrote down this action, and, you know, Eduardo likes to ask, is it gauge invariant? Okay, so let's ask, is it gauge invariant, right?
Except that the validate.
Right, okay, good. So you know the answer, so you're not going to ask about this one, right? But okay, so under gauge transformations, A goes to A plus partial alpha, okay? And the point is that the way that you show that it's gauge invariant involves integrating by parts, right? And so you can do this calculation. It's not hard. But basically, suppose that I impose periodic boundary conditions in the time direction. That just means that I'm imposing that t equals minus infinity and t equals plus infinity. I have the same state. And I'm also going to impose them in the x direction. But I'm going to have open boundary conditions in y, right? So let's just do, here. Here's my spatial slice, y equals 0 is my boundary, okay? Then what you find is that this action changes by a boundary term. So when I say integral over y equals 0, I'm integrating over, over x and t on this boundary here. And it has the form a0 dx alpha minus ax dt alpha. Okay. So what do we do? Well, that tells us that at this boundary, see if I can find it. Okay, okay, so what do we do? So that tells us that at this boundary, we need another theory. So we need somebody at the boundary to cancel this anomaly. Okay. And, I could think of A as a background gauge field in which I'm saying that, if I want to preserve the symmetry, this is a U1 symmetry in this case, U1 charge conservation. So, if the background gauge field, then I have to cancel the anomaly or I break the symmetry. Obviously, if this is a gauge field, if you want to gauge it, then you better cancel the anomaly or you've done something horribly wrong. Okay, good. So who cancels this anomaly? Well, to our rescue, we will add the boundary action of a chiral boson. Okay. And, I could add some velocity terms if I wanted to. Those are not so important, so, we can, for now, I'm just going to ignore this, okay? And this has a conserved current, right? By the equations of motion. If I have J0 k over 2 pi dx phi, then, and this has, okay, so let me set v equals 0, because this is what I have in my notes, okay? So maybe we'll erase this term. I could modify this. Okay, but if I just have J0 as dx phi, then by the equations of motion, right, d0, J0 is equal to 0, right? Take the variation with respect to phi, and that's what you get, okay? And so this is a conserved current which has Jx is equal to 0, okay? So now if we gauge the symmetry, so remember, when we gauge the symmetry, we just want to couple the gauge field to the conserved current, okay? So let's couple to some gauge field, a mu, in 1 + 1 dimension. And so if I do that, so I'm switching back and forth between t and 0, for which I apologize. I'm going to go back to 0 to match my bulk Lagrangian. Okay, and so somewhere, right, so what it means to couple to the background gauge field, or to the gauge field, background or not, right, is I have to write a term a mu j mu, and that has just a0, right, dx phi. And if I like, okay, and I'm going to do this for convenience, I can add some other terms to the action, right? And in this case, it's convenient to add a term a0 ax, okay? Because remember what John said, that, the anomaly is kind of the part that you can't kill by adding, local terms that, gauge invariant or not, right? And so the expression for the anomaly, like the actual, kind of expression is not universal, so it's convenient to add this term so that it's going to match up with what I had before, okay? And so, so now if you do this, right, you find that, well, this action is definitely not gauge invariant, okay? And specifically under gauge transformations, if I write this down, I find that the variation in the action looks like this. And this is great because, yes, this is what we need to cancel the bulk anomaly.
Sorry, could you repeat the anomaly that John mentioned in his lecture, that the Chern-Simons theory has this U1 form symmetry that is anomalous?
This is not a one-form anomaly. This is an anomaly of the, so this, because this is just like an ordinary zero-form U1 symmetry. Yeah.
So
Are
does
you,
it make sense to say that is the anomaly associated with some symmetry in the book?
yeah, that's right. So basically, like, I have the fact that I write down this action means that I am, so either A is, an honest to goodness gauge field, so then I have a U1 gauge symmetry, okay? Or I could say, well, this is some kind of bulk response action for some background gauge fields, right? That are described, but those background gauge fields are, like the fact that this is a U1 gauge field means that there's a U1 symmetry, okay?
Another way to say that is in the bulk, it seems that there is a current that goes through the boundary, and it's going to end there.
Yes.
And it's actually absorbing the boundary.
Yes, good. Yeah.
So charge conservation is preserved.
Yeah, so why do we call this anomaly inflow? Well, there's a picture, right, where I have, this kind of phi theory on the boundary doesn't conserve charge. The bulk also doesn't conserve the U1 charge, but, basically, like, the charge that is appearing at the boundary is coming from the bulk. That's why we call it anomaly inflow. So this word was first used in a quite classic paper by Callan and Harvey. They were talking about, string defects in 3 dimensions, but it's the same concept. Good.
Actually, an example in 2 plus 1 in the paper.
Oh, okay.
Which in a sense is
All right, good. Okay. So this is the case if I have a single Chern-Simons theory. So what about doubled CS, right? So now I have my, this is A dA1 minus A2 dA2, okay? So the natural way to start talking about the edges is to say, well, look, okay, the edges that I can have here should be things that I can make out of the, the chiral boson associated with this guy and the chiral boson associated with this guy, right? And so I should have something like 2 over 4 pi, okay? And now I'm just going to have a phi 1 d0 and a phi 2. And this is a, let me do it like this. This is not a squared, this is a 2. Okay, good. All right. And now if you like, you can change variables, okay? So again, you can do the algebra yourself, okay? But basically, when you do this transformation, you get a 2 over 4 pi dx theta dt phi. Okay. Now, when I write down this guy, right, it's pretty clear. So basically, this says that the derivative of phi is the variable that's canonically conjugate to phi, okay? So it's pretty clear that writing down a potential for phi is, going to be pretty hard, right? Because phi and d phi don't commute, and so, if you try to add some term like cosine phi, okay, it's not going to want to have an expectation value. However, here, there's no such obstruction because it's, because now I have a theta and a phi. So the fact that I have these two guys means that, and I could add velocity terms, none of this really changes qualitatively. So this edge is gappable. And explicitly, it can be gapped by adding terms of the form cosine of theta or cosine of phi, okay? Now you have to be a bit careful, okay? So, it will not be gapped by adding things like cosine of theta plus or minus phi, right? Because these guys actually either just have phi 1 or just have phi 2, okay? And remember, phi 1 does not commute with dx phi 1. Good. Okay, so this is a gappable boundary, but you can ask, what about the symmetry, okay? And I'm not going to go through the argument of how you actually figure out how the symmetry acts on this edge. Levin and Gu do this in their paper by basically working with an explicit spin model of the boundary in which they can figure out the symmetry action, and then identifying the lattice variables with the continuum fields here, okay? So the conclusion of that is that under the Z2 symmetry, so that story I'm not going to tell you, but under the Z2 symmetry, what you find is that both theta and phi actually get shifted by pi, okay? And so what that means is that if I want to gap the edge in a way that's invariant under symmetry, that's symmetric, right, I'm not allowed to write down just cosine theta or cosine phi, right? These guys are out because they're going to change sign under the symmetry action. Now, I can write down cosine of 2 theta and cosine of 2 phi, okay? But this factor of 2 is important, okay, because theta, and I didn't sort of explain this, but we've chosen all our coefficients, okay? So theta is a periodic variable, as is phi. Okay, so these guys are degenerate. Okay, because there's 2 values of theta that would be, that would have the same energy. In other words, what that means is that these are what we call cat states, Schrodinger cat states, right? So these would be like the all up plus all down states.
Wait a second.
Something like that.
You can write cosine 2 theta or cosine 2 phi.
Yes, I can't write both. Yeah, I'm going to pick one or the other of them. Yeah, that's right.
You write cosine 2 theta is presumably irrelevant.
So, okay, good. So,
It's a critical value.
yes.
We normalize a theory, effectively.
No, but what I'm saying is actually stronger than that. So you're right. The first thing is like, if I weakly perturb the edge by a cosine 2 theta term, is it going to gap? Okay, and that's the question that's answered by the question of is this relevant or not. But what I'm saying is a stronger statement. I'm saying I'm going to come in, okay? I'm going to come in with some big perturbation. I'm going to, take your edge and I'm going to proximatize it with some other material, okay, that's going to like add a cosine 2 theta term, and it's going to be really big, okay? So now it's relevant. I made it really big, okay? So it will gap the edge, But what I'm saying is, either you generate cosine theta, in which case the edge is not invariant under the symmetry, or you're going to generate cosine of 2 theta, but now there are 2 degenerate ground states. Right. So that's the statement. Okay? And this aligns exactly, right? Exactly with our definition of SPT. There is no unique, symmetric, gapped ground state at the edge. Yes, you can. You can break the symmetry. That's right, that's right. And that's the big difference, right? So that's the big difference between these edges here. So this is a Z2 one, but this is also, it's kind of very similar to what you would say for quantum spin Hall, right, with time reversal symmetry. That's the difference between this and this guy here, right? So here we know that there's a topological, even if you don't care about symmetry, there's a topological obstruction to gapping the edge. Okay. Good. All right.
Quantum spin Hall, people say that the SPT remains coupled.
In quantum spin, well, so quantum spin Hall is also an SPT, right? And so, so the edge is gapless, provided I don't break the symmetry, right? Because like these guys can be symmetric, but again, the fact that they're degenerate, okay, in a 1D system, that means that you have a cat state. So this degeneracy you should think of as indicating that you have a spontaneous symmetry breaking. Okay, yeah. Okay, good. So that was my, so that was my review of the tale of 2 paramagnets. And again, I want to point out that we have these 2 different perspectives on what it means to be an SPT. We have this anomaly inflow perspective, and we have this braiding statistics perspective, right? They both sort of describe the same thing, okay? So now, I would like to, again, sort of take this beyond the context of ordinary symmetries and topological orders and talk a little bit about the questions for subsystem symmetry, kind of instead of our, subsystem global symmetry instead of our ordinary 0-form global symmetry, and fracton topological order instead of ordinary topological order. And I would like to know the following things. Are there SPT, we call them subsystem symmetry protected phases, so do these exist? And if they do, how do I diagnose them? Can I think about anomaly inflow arguments? Can I think about braiding statistics? Arguments. Okay, good. So the basic answer to all 3 of these things is yes, okay? And so maybe what I'll do in the time that remains is I will give you a simple sketch or an example of anomaly inflow. Okay. This is in a paper with Hotad Lam, Shuhang Shao. I do not remember actually the author order. I think it's something like this. Okay. Anyway, so in this paper we give a lot of examples. I'm just going to give you one, okay, to show you that actually the anomaly inflow that we get, for example, in the BF theory of our line-on-planar model, really works very much the same way as it does in this Chern-Simons theory. Okay. So let me just do this example. Okay, so let me remind you that when we talked about the line-on-plane-on model, we wrote down a BF action that looked like, I think there was a 2 here, okay? But let me call this like sort of K, and we're gonna maybe just think about the analog of an ordinary quantum Hall state, okay? So we're ultimately gonna take K equals 1, but I could write this action for any K. Okay. So now we can play the same game, right? We notice that when we go to show that this action is gauge invariant, the way that you would do it would involve some integration by parts, okay? And so for example, I think the most interesting case is let's take periodic boundary conditions in X, Y, and T, and open boundary conditions in Z. Now this model obviously is quite anisotropic, so the fact that I'm choosing Z gives me a particular choice. That's the one I'm going to talk about today. Okay? So if you do this, what you find is that the action changes by a boundary term. Okay, so the integral over Z equals 0. Okay, and beta is the gauge parameter for my B gauge field. Okay, and I get this term here, and boy, it looks pretty similar to this term here. Okay. So once again, we're going to do the same thing. Okay. We have to find a theory that can live. Now, okay, sorry. Let me point something out. Okay. Let me point something out. So this, here I have a sort of BF or mutual Chern-Simons term, right? Okay? And what I notice here is I've chosen this to be gauge invariant under A goes to A plus some definition of D alpha, right? These are the appropriate derivatives. But when I did that, I sacrificed the gauge invariance, okay? I had this boundary term for B goes to B plus D beta, right? So I sacrificed the gauge invariance of B. Now, obviously, I could have, written this action in a way that would have been totally equivalent in the bulk, where it was gauge invariant under this transformation, but not under this transformation, okay? But you can convince yourself by try enough things, okay, that you can't get rid of this boundary term for both A and B simultaneously, okay? So this is so this is an example of what we call a mixed to Hooft anomaly in the sense that we can't, our boundary theory rather, let me just put it this way, our boundary needs a mixed to Hooft anomaly in which we cannot gauge A and B simultaneously. Okay, so it's just going to look a wee bit different than the Chern-Simons example. So what kind of theory does that? Well, my boundary action, I'm going to have a scalar field. And it's going to have a very ordinary action. This is sort of the most obvious action you might write down for your scalar field, right? If it was in one dimension, I would erase the dy, and this would be like our favorite, just boring, most boring scalar field action. And here I've got the dx dy, and that's because this boundary, we want to preserve the subsystem symmetry. Okay. And so this, and in particular, this subsystem symmetry means that I can take phi and shift it by any function of x and any function of y. Okay. Good. Okay. And so this is a global symmetry. It has a conserved current, which is one of these sum-system symmetric currents. Okay. And again, these are conserved by the equations of motion. Okay. And this is the guy we're going to like couple to A. Okay. But this actually has another current that is conserved. So I could have called J twiddle 0 dx dy phi, and I could have called J twiddle xy dt phi. And this is also obviously a conserved current by equality of mixed partial derivatives. Okay. And okay, so these guys have, this guy is often called the momentum symmetry and the winding symmetry. That's right. Yeah, so both, good, thank you. Both satisfy d0, j0 minus dx dy j xy equals 0. I think, okay, yeah, you can check whether this is a plus or a minus, but there's a current conservation law that looks like that. Okay, good. Okay, very good. Okay, so now we would like to gauge these symmetries, right? So how do we gauge them? Well, this first symmetry here, you do it kind of in the obvious way. So remember, when I gauge it, my philosophy is what I need to have somewhere in the action an A mu, J mu term, okay? And so this one, you just do it with the usual canonical momentum, right? So d0 phi squared goes to this, dx dy phi squared now goes to dx dy phi minus axy, okay? And because these guys transform like if you like in terms of your ordinary bosonic fields, these guys transform like the phase of your field, okay? And so this is like the analog of the canonical momentum. But now if I want to gauge this guy here, oh, yep, I better square that, thank you. So if I want to gauge this guy here, right, I need to add a term, right? I'm gonna have to add a term that looks like, here we go, 1 over 2 pi, b0 dx dy phi. So this is b0 j0, right? And here I'm going to choose this to be gauge invariant under, again, the gauge transformations of A, right? But we'll see that it's not invariant under gauge transformations of B. Okay, great. So this is my action. Like I said, this is how I should couple my fields to, this is how I should sort of gauge the symmetry, okay? And you can see that the change in the boundary action, okay, so here I've got 1. If I replace 1 by k, right, there would be a k. But anyway, you get a 1 over 2 pi. And then I get a beta, the gauge, right? B goes to B plus d beta, where d can have these x and y derivatives, okay? And then we get exactly what we want, which is d0 axy minus dx dy a0. Okay. So anomaly inflow, basically works, and it works more or less the same way. And I presented this case because it's sort of the cleanest one. There are other examples of this in various places in the literature. Can you turn the slides on up there? Now we'll see if they're listening. Okay, so what I want to tell you about next is, so this was this anomaly inflow, okay? Oh gosh, and you might, yeah, so this is anomaly inflow. And you might now I want to ask a little bit about, well, what about this braiding statistics argument? And in particular, what does braiding statistics tell us about what kinds of, sort of SSPT-like phases we can have? And so the general inspiration here, right? The general inspiration is that I want to think about what I did to get from the toric code to the semyon model, okay? And the word that people like to use for this is twisting. And what twisting means is I want to choose a particular sign structure for my sort of generalized domain walls, okay? And so what I'm just going to show you guys some pictures, okay, of how this works in a model which actually has subsystem symmetry along all three planes. So this guy here, this is a construction of a model that has subsystem symmetry. Okay, so the charge is conserved in the xz, the yz, and the xy planes. This is what we call a sort of three-foliated order. Okay, and there is a way to do this. And like I said, I'm just going to show you the pictures. I'm not going to explain the details, but you can, basically, you're playing the same game. We played the same game as Levin and Gu did from the toric code. Okay, so we found a spin model, okay? The spin model, looks a bit complicated. We actually have spins at the corners and then sort of dipoles of spins living kind of at the centers of these cubes, okay? But you can do this. And so when you have this kind of planar subsystem symmetry, okay, you should sort of think of it as it takes everything down a dimension. What that means is that normally if you had like a spin model in 2D, you'd be like, well, my domain walls are surfaces, okay? But with subsystem symmetry, your domain walls basically have this line-like character. So we call them like domain frames or domain cages, okay? And in this model, you actually have two different kinds. So, for your ordinary spin, you have these blue cages, and then we have these little sort of square cages for the dipoles. Okay. And there is a Hamiltonian that you can write down. Okay. And my collaborator Yushiyu, and I think this actually made it into the paper, but at some point in the draft, it was like, this is this Hamiltonian of unspeakable horror. So it's very complicated, okay? But it does the job of having the right sign structure, which in this case turns out to be that when you get these little sort of corner domain frames, you get a minus sign. So this is supposed to be, yeah, it's okay. So you have these like domain cubes, and then you have they sort of get sewn together by these little corners. And the corner, when you add a little square, you get a minus sign, okay? Why is that relevant, okay? Well, just like I showed you for Levin and Gu, okay, there's a kind of a heuristic argument, and you can verify this by like, kind of building the operators that create these symmetry fluxes in the bulk and compute, or going to the gauge theory of fractal order, building these excitations in the bulk, computing the commutators of the operators that create them, okay? But the heuristic argument works exactly the same way. So these guys, because of the subsystem symmetry, okay, it's not a picture of a planar twist, it's actually a picture of this sort of twist of this box domain frame, okay? But the action is happening here, that basically I'm shifting one of these little square plaquettes around in going from left to right. And in doing that, I get a minus sign, okay? And you can argue, and like I said, I think the careful way to do this is like looking at commutators of the operators that create these things. You can argue that this is a kind of self-statistic that you should think of as telling you that these guys are a bit like semyons, okay? So now you can ask, can I make this braiding statistics argument for these guys? So we can look at their self-statistics. And again, so this, these purple dots you should think of as being on the boundary. Okay, I'm working in the symmetric phase. I have these domain frames. They're not going to end in the bulk. But they can end on the boundary, right? And because they can end on the boundary, I can essentially play. This is sort of a picture of the analog of the argument of Levin and Gu, right? That shows you that at least when you create pairs of domain frames in the same layer, okay, you have a kind of an obstruction to realizing a trivial gapped boundary. Okay. Oh, good. Okay, that's the end of the slides. So maybe let me Okay, so in the last sort of 5 minutes or so, maybe I'll tell you a little bit about what this boundary is, because I think it might amuse some of you, and then I will gesture at a case which actually is related to this line-on-plane-on model that we have been talking about so much. Okay. So you might ask, can I write down some kind of theory which has, by which I can deduce a boundary action using anomaly inflow, okay? And the answer is basically yes, okay? And the action is in our paper, but basically what this suggests is that the boundary action should look like this. Write it like this. And this is a boundary at z equals 0. So this is a boundary that lives in the xy plane. So you see x's and y's and not z. I have a single scalar field, and the action looks like this. Okay. Okay. And what is this? Okay. This just looks like, we could call this capital phi y. This is a dipole oriented in the y direction, okay? And I could call this capital phi x. So this is a dipole in the x direction, right? And this looks like, right, so this is proportional to dx capital phi y, d0 capital phi y, minus dy capital phi x, d0 capital phi x, okay? So when we do this anomaly inflow type argument, which you can actually do directly from the lattice model Hamiltonian to kind of infer what terms you should have in your Chern-Simons action, okay? You conclude that the thing that lives at the boundary is a bit like chiral scalar fields, but it's now a theory of these dipoles, right? And we have y dipoles that are somehow moving chirally in the x direction, but also x dipoles that are moving chirally in the y direction. Okay, good. Sorry? Yeah, that's right, that's right. So I think, again, this is a bit like, this interpretation, I would say, going from dy phi to capital phi y is very natural on the lattice, right? Let me just say, because on the lattice, dy phi, right, is just this little object, right, that has, a plus here and a minus here. Okay, so it's like a dipole. In the continuum, I think this interpretation is more delicate. But it gives you a picture on the lattice. Good. Yeah, it's the theory in the boundary. Yes. Cancels the anomaly. That's right. That's right. Okay, good. So John is sort of saying it's very floppy, and I think so that's a feature of having the subsystem symmetry. So like even the thing that I wrote down before, like dx dy phi all squared, right? If you look at its dispersion, it has lines of 0 at kx equals 0, ky equals 0. So this floppiness is definitely a characteristic of these subsystem symmetric phases. And you might ask, so the other thing I should say about this is, although this looks a little bit like we're, got something going on with some chiral scalar fields, there's not, an analog of a thermal Hall, like, it's not a sort of topologically protected gap boundary. It's a symmetry protected, topologically protected gapless boundary. It's a symmetry protected boundary. Does it?
Lines and zeros.
Oh, the disparate, yeah. Yeah, good.
Used to be called the Bose method.
Yeah, so I would say these lines of zeros are in a very particular pattern that has this subsystem symmetry quality, but yes, I thought Bose metals often had Bose Fermi Bose surfaces or something, but yeah. Okay, and then maybe let me just make one last comment, okay, which is, and then I'll point you to a paper if you're interested in this. So basically what we've learned is that yes, we have anomaly inflow type arguments when we write down, for example, these BF-like actions which are relevant, or self-Chern-Simons actions which are relevant for many fracton orders, okay? Yes, we have anomaly inflow. Yes, when we have something like a self-Chern-Simons term, we can generate statistics between symmetry fluxes. And yes, that those guys really do have, symmetry-protected gapless boundary modes, exactly like in 2D. Now, the very last thing that I want to say is that this guy had a feature, right, that the statistics were really all between guys in the same plane, okay? And it turns out, it was later, figured out that means that you can kill, okay? Turns out you can kill the gapless boundary okay, by coupling in stacks of lower dimensional SPT phases. And I should say two-dimensional, little d, okay? Two-dimensional SPT phases, okay? And so this is, one nice way to think about fracton orders is you can ask, well, how much of the fracton order is robust? Not just if I, kind of am allowed to make like local, perturbations semi-Hamiltonian, but if I'm really allowed to kind of like sew in stacks of, say, two-dimensional systems and couple them in whatever way I want, okay? So this is an example of something that's not robust, okay? But there are also examples of SSPT phases, okay, that are robust to this business of stacking on lower D systems. And maybe I'll just point you to the paper. It was by Trithep Devakul, Dominic Williamson, and Juven Wang. Okay. And the basic point that they make is that if you look at the way that these braiding statistics work with subsystem symmetry, okay, and you sort of think about the braiding statistics of dipoles, okay, it turns out that, so let me sort of draw a line, okay, connecting the, symmetry flux in layer K to symmetry flux in layer K plus 1 and layer K minus 1, okay? And I'm going to draw a line if they have a certain non-trivial braiding and no line if they don't, okay? And it turns out that basically there's a sort of, conservation of this symmetry flux, okay, that these lines can't end. So this is okay, right? If maybe I have two different symmetries on each layer, right? So this, this kind of cross pattern, this kind of cross pattern is okay, right? But for, say, a Z2 symmetry, I have to have an even number of lines coming out of each site, okay? So this is okay. What's not okay would be something where, I sort of end this line, okay? And what that means is basically if I look at the braiding statistic between a dipole that looks like this, okay, starting at layer Z0 and going to layer Z0 plus 1, and a dipole between, that goes from layer Z0 down to layer Z0 minus 1, okay, this statistic actually pulls out the translationally invariant pieces of these lines and diagnoses what we call the strong part of the subsystem SPT phase. Okay, so I just wanted to gesture towards that, and I'll end there, and I realize we're a bit over time, so. I think people want lunch.
For lunch, and let's recombine here at 3, well, a few minutes before, so that we can have some announcement. And we thank for the nice lectures. Thank you.